Hello everyone, in this video I'm going to discuss broadband matching by multi-section quarter wave transformer. The method that we eventually use will be binomial matching network. Okay, I hope this is clear enough. So I will switch you to book view. Now, before moving forward, let's review what we have learned from quarter wave, single stage quarter wave transformer. We know, right, the bandwidth is not going to be good. The left side is the part of the reflection coefficients against frequency. And you can find out the actual max occurs in only one frequency, F0. If the frequency is slightly deviated, then you are going to have lots of reflection. Say for example, if you are here, then the reflection will be that much. If you are here, then the reflection will be huge. So we know that the quarter wave transformer has the characteristic impedance given by square root of Vs times Vl and we also know that Vq is always real. Normally. Like what I said, the refraction coefficient plots against frequency is very ugly. Too sharp here. And before moving forward, let's review the formula for one quarter wave transformer. We are going to look at the bandwidth. First, in terms of impedance, at resonance, the length of the quarter wave transformer is exactly 90 degrees, which means pi over 2. At this frequency, at this wavelength, the reflection coefficient is lowest. But what if the frequency is slightly off? It's not going to be equal to pi over 2 anymore. So let's assume beta L is equal to a certain angle. This angle is definitely not pi over 2. And from the source side, we know that the input impedance is given by this amount. This is the source input impedance. And we also know that the reflection coefficient can be calculated at this point here is d in minus d naught the source impedance, and then like this divided by d in plus d naught. Yes, that's it. So if we substitute d in into this formula, let's take a look what we are going to get. We do that, and then do a little bit of simplification by merging this merging these two together, and then we take out the tangent term. This is what we get. And after some simplification, you will get a very clean formula where you have at the bottom, VL minus VS plus J2 times tangent theta and then times the characteristic impedance of the quarter wave transformer. Now, if we move on, continue to work out to derive this, we don't just stop here. Then you will notice after some more simplifications by moving the term to the bottom and then extract some, expand it. Then you get the left side where VL plus VS can be expanded like this. Yeah. We can just add 2. Yeah, I was wondering why there's a minus here, but I forgot to look at this term. And then we will get this formula. And remember, at the bottom, we have secant square of theta, where theta represents theta L, the length of the quarter wave, the electrical length of the quarter wave transformer. And we can rearrange this equation in such a way that secants of the theta L can be expressed as a function of refraction coefficient. Okay, let's move on. Now, on the other hand, we can also, instead of putting gamma, the absolute value of gamma against frequency, we can also put the gamma against theta, where the horizontal axis will be replaced by the electrical wavelength. At exactly the resonant frequency, we know the length is going to be pi over pi over 2. Yeah, you get it wrong here. This will be pi over 2. So I change it. Here should be pi over 2. Making a mistake. Okay, yeah, let's move on. Let's move on. Let us move on next to this slide. Yeah. Okay. So we know that when it is very close to this point, secant square is much greater than 1. And in this case, you may have shown the refraction coefficient to be this value. I'm now talking about this formula. From this formula. This one. When theta here, when secant theta here is very large, then this one is meaningless because secant square is almost trending to infinity. So in this case, the value here will be like this. So this is a formula for the situation, for the condition where the frequency is very close to the resonant frequency. Now let's take a look in a situation where the frequency is not close to the resonant frequency. And let's also assume that this frequency, this electrical wavelength corresponds to a refraction coefficient, gamma m. So I'm now talking about this formula. When beta A is equal to beta m, beta is also equal to pi minus beta m. So using the previous equation that we developed from the previous page, we can substitute gamma as gamma m and beta as beta m for this formula. And we can rearrange and we can extract the cosine beta m, and the formula is that simple. Let me see. Yeah, alright. I'm going to use okay, we are going to look at the next page. The larger the value, the ratio, low impedance to the ratio of low impedance to the source impedance, then the beta m will be larger. Equivalently, when beta m is smaller, then we will have more narrow bandwidth. Okay, let's introduce another concept, fractional bandwidth. Fractional bandwidth, first, beta is equal to beta L, and where beta L is 2 pi omega divided by the velocity. This is the formula. At resonant, we know why beta is equal to pi over 2. So if we look at the ratio, beta m divided by the resonant electrical wavelength, then we will get beta m divided by pi over 2, which corresponds to Fm divided by F0. F0 is the resonant frequency, where Fm is the frequency slightly off from the resonant part. And we can work out the value of beta m based on this formula. And also, our target is to work out the bandwidth. The bandwidth is delta F divided by F0. Delta F is the frequency, upper frequency minus the lower frequency, as I said here. The delta F is equal to F0 minus Fm. Fm is one side of the frequency, one of the corner frequency, and we just get the difference and then multiply by 2, and this is delta F. And if we do a little bit of manipulation, it is equal to this value. And 2 times Fm over F0 is equal to like what I have found out here. Yeah, 2 beta m divided by pi, and if you multiply by 2, then it's 4 beta m divided by pi. So we have a very clean formula. Previously, we have already worked out beta m. Beta m is the exchange of expression in terms of gamma, and this is what we get. Now, this is the formula for the fractional bandwidth of one single stage, one quarter wave transformer. And here, what we can see is we can do further manipulation, and this is the core objective of this chapter. Now, we can have a multi-section quarter wave transformer, and you will make a huge difference. For example, now you are having one quarter wave transformer, and I'm going to show you the situation when you have two quarter wave transformers connected together and see what is the difference. And in terms of bandwidth, you will see that by looking at the first version frequency, the blue characteristic represents the reflection coefficient as a function of frequency. It is super sharp. For the one single quarter wave transformer. The pink one represents 2. So you can see there is huge benefit. The bandwidth is at least much larger. And this is the Smith chart. I don't think you can see anything from the Smith chart. Let's move on. Now, clearly, you can modify. You can add more quarter wave transformer in a way to broaden the bandwidth. And this is the core objective. And there are many methodologies where you can broaden the bandwidth. One of the ways is binomial matching network. And it is also the algorithm, the methodology has been used for Butterworth builder. So before moving forward, let's take a look in the multi-sections quarter wave transformer. Just like in this case, I have B section connected together. N section. N section. There is the first V, and then followed by many other identical quarter wave transformer. All of the quarter wave transformer had the same length theta. And all of them contribute a reflection coefficient. But as far as the input from the left-hand side is concerned, the reflection coefficient is given by, it can be divided, but the derivation is out of scope in this slide. It can be calculated under the theory of small refractions. The total reflection coefficient that you can measure from the left end of the quarter wave transformer trace can be approximated in this formula. There you have theta naught, and then the next stage, theta 1 times e to the j times 2 theta, and then followed by theta 2 times j 4 theta, and then and then when we just move on forever. So this is the total reflection coefficient calculated for multi-sections quarter wave transformer. And this multi-section quarter wave transformer doesn't have to be the Butterworth. It doesn't have to be a binomial level. Okay, now I'm going to turn your attention to binomial matching level only. According to equation 3, you can change the individual reflection coefficients for a particular quarter wave transformer between the quarter wave transformer strengths in a way to minimize the total reflection coefficients. And one of the ways that you can try is to use binomial formula. A times 1 plus x to the power n, where x is equal to e to the power minus j2 theta, 2 times the electrical wavelength of each quarter wave transformer. Now, recall what we have done previously. The total reflection coefficient that you can measure from the source is similar to this one. But this one is not divided by the previous formula for theory of total reflection. Instead, we just multiply this by n times. And this is what we are going to get. Where C of n0 here represents n choose 0. In this case, n choose 1, n choose 2, n choose 3. And the overall formula is like this. And you don't really need to memorize or even use formula to calculate the individual coefficient. Now, you can use the Pascal triangle to work this out. And of course, if you like, you can still use this formula. Now, let's look at the previous formula. Now let's take a look here. Let's take a look here. Now let's take a look. What if theta naught is 0? If theta naught is 0, then e to the power 0 is 1. Then the sum of this guy here is a times the sum of this. And this is what I want you to know. Yeah. If theta is 0, then you can calculate this. Then remember this reflection coefficient is the sum of the this n choose 1, n choose 0, n choose 2, blah blah blah. When you add all of them together, then you will find A. But when the electrical wavelength is actually 0, you know how to calculate the reflection coefficient. It's just VL minus V naught divided by EL plus E naught. So the left side of the equation is done. The right side, A times 2 to the power n. Perhaps I need to tell you how we can get this. Yeah. Remember, I told you before, when theta is 0, e to the power 0 is 1. So 1 plus 1 is 2. And that's why 2 to the power n. So this is what you get. And from here, you can work out the value of a. And remember, x minus 1 divided by x plus 1 can be approximated as half lnx. So the formula here, EL minus D naught divided by EL plus D naught can be replaced with this formula. Because of this, you substitute here, then you will get this. Now we are going to look at the situation when theta is not 0. The electrical wavelength is not 0. Under this condition, it's not 0. We just this value times a times this. We substitute a here with this. Now, if we just take a look in this series, yeah, this summation sign have multiple terms. If you just look at just one term, and the index value is n, and you will get this. Gamma n is equal to this one. Okay? So remember, the total reflection coefficient from here can be calculated using I'm going to show you in the next page. Theta n is equal to this one. So gamma n is equal to the next impedance minus the present impedance divided by the impedance of the next stage plus the impedance of this stage. And if you simplify this, you will get this. And of course, you can use the x minus 1 divided by x plus 1 approximation using the formula. So you get this. And what we can do now is we equate the sum of this. What we are going to do is this 1 over 2, we move it to inside the bracket, and this 1 over 2 to the power n plus 1, we move it to inside, and we move this as well, and eventually we got this formula. Then if you equate the parameter inside the log brackets, then we will get this. So this formula is very clean. You automatically know the impedance of the next stage. All you need to do is to find out the source impedance and the load impedance. And you can even reverse it. Instead of having the low impedance on the top, and the source impedance at the bottom. You can also uh, put the source impedance on the top and the low impedance at the bottom. In this case, you just reverse the result. It will work both ways. Now, let's take a look in the fractional bandwidth for the binomial matching network. At least we want to know how much better we can get. So let's recall what we have learned from the formula. You can rewrite this formula. Yeah, you can restart with by extracting e to the minus j theta out, and then you can see right, this is just 2 times cosine theta. This is what we get. Yeah? And if you focus on the magnitude only, the magnitude of this one is always 1. The magnitude of A is A. The magnitude of this term, is cos to the power n and e a here and 2 to the power n. So we can get the magnitude of the reflection coefficient in this manner. And let's define the total reflection coefficient. I mean the maximum total reflection coefficient, gamma m. And then we just do some calculation. And for example, this one we replace the theta by theta of m, and then gamma by gamma of m. We got this formula. And with a little bit of rearrangement, get the arc cosine, and then this formula. And we use the formula given in 2A for the binomial matching network. Then we know 2 minus 2 pi divided by times theta of m. Your theta of m can be substituted with this expression. And we call the value of n. So we call the value of a. A is just this value. So this is how you evaluate the reflection coefficients. Okay, let's take a look at an example. Suppose you are going to match a network 50 and 100. The low is 100 ohm. The source impedance is 50. And using the formula for binomial matching network, we can just substitute here. Right? 2 to the power n here is A. And this formula can be used in whatever manner you like. And then the first impedance is 50. And we are going to calculate the E of n plus 1. So when n is 0, then you get this. And you can calculate E of 1, 54 times 5. And when n is 2, you can calculate this. The final value is 70.7. So when n is 2, I got it wrong here. When n is 2, we got this. So altogether, you have a quarter wave transformer with, a binomial matching network with three stage, three stages. The first impedance is 54, the second one is 70.7, and the final one is 31.9. The value of A, let's do some calculation, is 0.04. And if you do this, you will find out the fractional bandwidth is huge, 0.71. On the other hand, if you substitute n is equal to 1 only here, then the value that you get is very, very ugly. The bandwidth will be very narrow. So you will notice the fractional bandwidth has improved by at least 50%, just by adding 2 more stages. There are other broadband matching network as well. One of the broadband matching network is tapered transmission line, and you have to use software to draw the tapered section. You will end up with a very low Q value, and normally the tapers are cleaned with computer-aided design software, so the total length is not going to be significant, and also it's quite manufacturable. Of course, it's just like any other tapered transmission line, it has some reflection. Okay, if you want to read more references, then one I would recommend is Professor Amitahu. But yeah. Okay, so if you have further questions regarding this slide, you can leave your question to the comment section. Thank you.